Hello everyone, thanks for watching this video. I'm Zhang Hanyi. It's my honor to give a presentation here. Today my topic is Adversarial Separation Network for Speaker Recognition. The presentation is organized as follows. Firstly, we'll discuss the research motivation and the related work. Secondly, we'll describe our method in this paper, named ASNet, the Adversarial Separation Network, including process overview, model structure, and loss functions. Thirdly, we'll demonstrate the performance of ASNet on speaker recognition system. At last, we'll summarize our contributions. The purpose of our work is to protect speaker recognition systems from adversarial attacks. So, what is adversarial attack? Generally speaking, it is an attack technique that deceives the target model by adding perturbations on natural examples. Nowadays, many studies have shown that adversarial attacks have greatly affected the security of identity authentication systems, including speaker recognition. Please look at this picture. It is a study of the adversarial attacks on speaker recognition system, and in this paper, others proved their adversarial toolkit, FakeBob is effective on open-source speaker recognition systems. Besides, the research on the right demonstrates adversarial examples can successfully deceive high-performance spoofing countermeasure systems for automatic speaker verification. The adversarial attack used in this paper will be introduced below. FGSM uses the reverse transfer mechanism of deep learning by calculating the gradient that maximizes the loss. Adversarial perturbations of FGSM can be generated. PGD also relies on the gradient to calculate perturbations. Unlike FGSM, PGD uses a multi-step solution. Through several iterations, final perturbations are generated. Momentum attack uses the momentum gradient to change the perturbation. DDN that decouples the direction and the norm of the adversarial perturbation can achieve misclassification with only a few changes. Next, we'll introduce our proposed adversarial separation network. Our inspiration comes from the principle of adversarial attack. Please look at this picture as shown in the red part. The key to a successful attack is the perturbation added to the natural example. So, as shown in the blue part, if we want to alleviate the threat posed by adversarial attacks, we only need to design a mechanism to separate perturbations from adversarial examples. Based on the above idea, we propose a separation mechanism. Moreover, to further optimize the ASNet, we design the compression structure and the speaker quality loss. Finally, we proposed the adversarial separation network that can reconstruct perturbations from adversarial examples and filter them off. As shown in Figure 4, the proposed ASNet consists of three parts, namely a perturbation reconstruction network (PRNet), a reality quality network (RQNet), and a speaker quality network (SQNet). The PRNet is designed as the compression structure to generate the adversarial perturbations for the input examples. It consists of compression and reconstruction module. The compression module is responsible for ensuring that the extracted knowledge efficiently returns relevant information on perturbations. The reconstruction module aims to improve the quality of reconstructed perturbations. The ArcuNet encourages the restored examples, which are perturbation-free, to be similar to real clean examples. The SQNet is the DNN to implement speaker recognition task. It is responsible for supervising the ASNet to generate the restored examples that can be recognized by DNN as the correct speaker IDs. ASNet's process overview is as follows. After the adversarial speeches are input into a system, the compression module of PRNet first extracts the relevant knowledge about the adversarial perturbations from speeches. Then, PRNet reconstructs the perturbation based on the knowledge. Afterwards, the results of the input speeches minus the reconstructed perturbations are the restored nature speeches. To make ASNet perfectly separate perturbations, three novel loss functions are introduced. The perturbation loss drives the reconstructed perturbations that close to the real perturbations. The reality loss encourages the generated examples to be regarded by ArcuNet as real clean examples, thereby improving the quality of reconstructed perturbations. We introduce the recognition systems DN as SQNet and guide PRNet's parameter learning through speaker quality loss. The effect of the speaker quality loss can be embodied as vectors pointing to the correct classes, which can greatly improve the embedding's accuracy. We tested the feasibility of our ASNet on the VCTK corpus to ensure the robustness of experimental results. We adopted two speaker recognition baselines and four types of attacks. In Table 1, the ERs of SeriesNet and SeriesNext on the different settings were evaluated. The results indicated that speaker recognition systems were vulnerable when attacked by adversarial examples. To systematically measure the performance of ASNet, we also employed other countermeasures, including adversarial perturbation elimination network, feature squeezing, and adversarial training. As shown in the data of Table 2 and 3, ASNet achieves relative error reduction rate of 79% on the different adversarial attacks. The experimental results proved that ASNet could effectively enhance the robustness of speaker recognition systems against adversarial examples. Besides, ASNet achieves relative error reduction rate of 74% compared with APGAN. The main reason is that ASNet adds a supervision mechanism for recognition results, which greatly improves the quality of the embeddings generated by DNN. Moreover, when recognizing FGSM, PGD, and MT, ASNet has 30% relative error reduction compared to ADV-train. However, when recognizing DDN, the relative error reduces by 63%. The reason is that the robustness of ADV-train is greatly dependent on the transferability of the adversarial examples in the training set. This causes ADV-train's performance to be unstable when dealing with different types of adversarial examples. The performances of adversarial examples with different perturbation intensities were also evaluated, as shown in Figure 5. While perturbation intensity increases, it is observed that the ER of ASNet is significantly lower than other methods, and this means that ASNet achieves the best performance under different perturbation intensities. We also carried out ablation studies on compression structure and speaker quality loss. It is observed that the relative error improves greatly after removing the compression structure. The model with no compression structure needs to perform transformations in the entire data domain, which makes model learning to be difficult. Besides, the results also show that after removing the speaker quality loss, the recognition system's ER also increases significantly. This is because the mechanism for supervising ASNet to generate examples that can be correctly embedded by the DNA is missing. The results of ablation study indicated that the two mechanisms could effectively improve the defensive effect of ASNet on speaker recognition systems. To sum up, we conduct adversarial defense research for speaker recognition systems, and the main contributions are as follows. We proposed an effective countermeasure to enhance the safety and robustness of speaker recognition systems against adversarial examples. We designed an architecture for the countermeasure, namely adversarial separation network, to eliminate adversarial perturbations and restore natural clean speeches. We further optimized the ASNet by introducing compression structure and speaker quality loss. Thanks for attention.